So this is looking at how we represent numbers, particularly positive and negative numbers, and different methods for each. Now there are 3 different methods at play here, so make sure you can separate the 3 of them. The first way we represent numbers in binary is quite simple. The lowest number is 0, the highest number is whatever the upper limit is. So in this case, the last number we got there is 0. Lots of zeros, and that simply equals 0. There's no rocket science to it. And that means that I actually can't use this to render a negative number. The high number, however, is 255 because it's 128 plus 64 plus 32 plus 16, 8, 4, 2 and 1. So that's 255. And that also means then 0, 1, 0, 1, 0, 1, which is that part there, 0, 1, well, 1, 2, 4, 8, 16, that's 32 plus 8 plus 2 is 42. All right, that's the meaning of life. So that's a really simple way, and this is how you know to render numbers in binary. But this system is limited. We can't render a negative number. So I'm going to show you 2 different ways that are used in binary to render negative numbers. And it's important to note, you will have to be told which one you are using, because you're going to get a string of binary and you're going to be told, what is this? And you can quite honestly say, if the question is, what is this? A bunch of 1s and 0s. What is this number if it's sign and modulus? What is this number if it's 2's complement? What is this number if it's a standard binary digit? That's fine. What is this if it's ASCII? All that's fine, but you've got to be told what your systeming is. So the next way we can look at, and this is how we can deal with negative numbers. We use a sign and modulus, it's called. The leading character, the very first one, the one most to the left, is a sign bit. 1 is negative, 0 is positive. And so that means if I have this value, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 1, that equals 1. It's not rocket surgery. But 1, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 1 equals minus 1. Now, when we think about this, there's actually 2 0 values too. If I was to go for 1, 0, 0, 0, 0, 0, 0, 0, that equals minus 0. And it's actually, there is a different number, 0, minus 0 to positive 0, equals minus 0. And if I look at it the other way, of 0, 0, 0, 0, 0, 0, 0, 0, equals positive 0. Okay? No, they're not, but they're different numbers. Yes, they are the same thing. Yes, they are the same thing, but they are different numbers. They are represented by different binary values, so therefore they are different numbers. Okay? Now that means if we're going to use sign and modulus, as we have here, that value and that value make our numbers different. And that means that we have the maximum value. Now, if you don't like that, you're going to hate this. The maximum value that we can use equals 0, 1, 1, 1, 1, 1, 1, 1. That's the maximum value. And it's 127. And because I have to do it, plus 127. I'll leave that out for a second. So the minimum value I can render, 1, 1, 1, 1, 1, 1, 1, 1. Equals minus 127. Okay? So the biggest value you can draw, you can make is actually not the biggest number you can create, if that makes no sense whatsoever. Just remember that leading bit there is a sign bit and 1 is negative. Okay? And for nerd programmers out there, Todd, this probably has come up in it may have come up to you, and I think, Lachlan, this may have come up to you as well. If you ever wonder why yes and no as Boolean values in a database are minus 1 and 0, that's why. So oftentimes if you've got a Boolean value as a yes, no, the integer value of that Boolean no is minus 1. That's why. Sorry?
It's not quite clicking in my head.
But that,
Sorry.
So it was not quite clicking. The fact that...
I don't know, I just don't think my brain was quite doing the thing.
All right, so just quickly the summary. You still have the same number part there,
Yeah.
and that's the same number part. So you have still you can count between 0 to 127. You can't go beyond that with 8-bit, with sign and modulus 8-bit, because this value, those values, indicate the sign, positive or negative. And it just so happens that the nerd who decided to define this defined 1 as being negative. As I said, I'm recording, so please don't say that. She says, download that one. Okay, so that's sign and modulus. And this will come up when we look at tomorrow, because tomorrow we're going to look at floating points, which is how we can deal with decimal numbers. I'm not going to deal with decimal numbers today, though. Give you this to go. Okay. Oh, floating points aren't that bad. He says that, yeah. Okay, so if I was to say to you, can you please tell me what minus 47 is, using sign and modulus, you'd think to yourself, I should start by drawing my number line. 1, 2, 4, 8, 16, 32. Now that's going to be enough. So 47, so I'm going to have one lot of 32 with 15 left over. That happens to be lots of them. So therefore my number will be 1, 0, 0, 1, oh good grief, I can't type. 1, 1, 1, 1, don't say it, I can't write. Thank you. Now, if I'm doing it in 8-bit ASCII, I'll add a leading 0, and I said minus. So therefore, what's my sign bit going to be? 1. So once again, there's a sign bit. And that's minus 47. Okay? Don't overthink it. It's the same as decimal to binary conversions, except the highest number you can get is up plus 127. The smallest number you can get is minus 127. And the part that freaks everybody out, there's 2 zeros. And I think that's the part that most people get confused by. You can have 2 values for 0. Sadly, when we look at floating points, you can still have 2 zeros. Okay. Now, just to confuse you, right, so Priyan just said there's 2, but yeah, I understand there's 2 values for 0. It's because that leading character, that sign bit, has 2 values, and the rest of it is 0. There's 2 values for 0. We'll look at floating points tomorrow. You can actually render a number using floating point operators bigger than infinity. We'll deal with it tomorrow. Ask Buzz Lightyear. Okay. Now, next. Shh, please. Next. Because that's confused you, I want to throw you another really confusing thing, another way of rendering a negative number. And we use this 2's complement method when we're doing binary arithmetic. Adding and subtracting and multiplying and dividing using binary numbers the way a CPU does it. Yes, but you have to understand how a CPU works. And by the way, you can whisper, it'll still pick it up. No, please don't. Okay, so what we need to do is, this time around, this is a different way of rendering numbers. So we've got sign and modulus. Now I'm going to show you 2's complement. 2's complement has the advantage of not worrying about a sign bit, and so therefore there's only one value for 0. It also means that you can, the lowest number is still going to be minus 255, kind of. Except you're not going to like the way it works. All right, so what we're going to do is we're going to start with my favourite binary number, 42. 101010. And we're going to work out what minus 42 looks like as a 2's complement. And it's a 3-step process, and it's really easy. Start with your number, 101010. Step 1, invert the 1s and 0s, 0, 1, 0, 1, 0, 1. Step 2, add 1. So this number plus 1, what's 1 plus 1? 10. And that's it. Simple. Invert the 1s and 0s. So every 0 becomes a 1, every 1 becomes a 0, then add 1. And that is 2's complement. And we use this in arithmetic. I don't know how to spell this word. Arithmetic, I think. Is it an E, is it?
How does it know that's a negative number and not just 22?
Because you have to be told. That's the point, and that's a really fair question. How do I know it's not 22? Because I've been told it's a 2's complement. It's like saying I've got this number here.
Doesn't that mean that all 2's complement numbers are negative then?
Yes, should be.
Okay then.
So I've got this...
An extra bit to tell the CPU that then?
No, because the CPU will know. So I've got this number here, 32. What is 32? Well, I don't know. So it might be, I have to put something on it, a prefix. I might have 32 litres, I might have $32, I might have 32, what's that word? That's euro. All right. So I need to be told, that's just a number. I need to be told what it is. And so is the same with numbering systems in binary. You need to know what the numbering system is. So when I look at 32-bit floating points tomorrow, I'm going to have 32 ones and zeros. And yes, it's as bad as it sounds. But the CPU will know that's a floating point operator and therefore treat it like a float. CPU knows this is a 2's complement. So it knows to make it knows that becomes a negative number. Okay? So the CPU will know up here that I have sine and modulus. And when you do your exams, more importantly, you're going to be told, this binary value is sine and modulus, or this binary value is ASCII, or this binary value is a number, which is to say the lowest possible value is 0, the highest possible value is whatever. This value is a 2's complement. You'll be told what it is and therefore have to know in your head, oh, it's ASCII, therefore I've got to read the ASCII table to get the letter value. Oh, it's a sine and modulus. The leading character is a 1, therefore it's negative. It's a 2's complement. I need to take the 1's complement and then invert. All right? You'll be told what they all are so that you'll be able to process that data effectively. You're not just going to be given a number and a binary string and say, here, what is this? Because you'd be very much entitled to say, it's a string of binary. Okay? And so actually when I throw the worksheet at you, you're going to get the same string of binary, and I'm going to tell you that if this is ASCII, what's the character? If this is a number, what's the number? If this is sine and modulus, what's the value? If this is 2's complement, what's the value?
There's a bunch of 10 people throwing a party. How happy are they?
You know, there are 10 people who understand binary. 10 people in the world, those who understand binary and those who don't. It's a terrible joke, thank you. All right. So, can we take a 2's complement number and work out what its value is? It's a negative number. Can we work out what that value actually is as a decimal number? The answer is yes, we can. Just do it backwards. So calculate the integer value of this 11000 yada yada yada. So the first thing you do, when you calculate a 2's complement, is you calculate the 1's complement and add 1. Do it in reverse. Subtract 1, then invert. Okay? So what's this value? 11001010 minus 1.
11001001.
11001001, I think is what you said, Todd. Is that right?
Yeah.
Yep, good.
Make it 00110110.
And then you invert it, 00110110. And we work out what's that, and that's exactly what, and you've just done it exactly right. So that's 2, 4, 8, 16, 32. 32 plus 16 is 48, 50, 54.
22 plus 32, yeah. 54.
And because it's a 2's complement, it's minus 54. Because we said this is a 2's complement, it's a negative number. It's minus 54. Hello.
Where is this used?
We use this in binary arithmetic. Now, this is really important to note. And when we look down here, you'll see down the side around here, if I can get the mouse to work around there, we're looking at binary arithmetic. It's really important to note that a CPU can do two things, add and shift. I'll explain the shift when we're doing it, but a CPU cannot subtract. So how on earth do you do a subtraction when you can't subtract? What do you do?
Add a negative number.
Add the negative number. What's the negative number? The 2's complement. There, and I'll show you the technique. That's not hard. Okay? You can't multiply because all the CPU can do is add and shift. How do you multiply? Add lots of times. Correct. The one that everybody hates, and I don't blame you, you can't divide. How on earth do you do a division when you can't divide? Shift and subtract. And I'll explain that. That one actually takes a long time to learn. Binary division is painful. I'll give you that one. It's very painful. But I'll show you how to do it. Right? And so where do we use it? We use 2's complement in arithmetic for subtraction and for division. Well, hold on. I'm going to give you a worksheet.
In the exam, which of those is most common?
All of them. Okay. So that's all I want to show you. So hopefully that recorded.